All right, so let's finish up this 12.4. So when last I left you, we were talking about this idea of a standard normal variable. So let's kind of refresh ourselves about what we're doing here. So the standard normal variable, we still want to think of it as a random variable. We're just going to use a z to really distinguish it from, just any other random variable that we have. So I'm going to look at this z and remember that it has the distribution function f of little z. Okay, so those are going to be, instead of x's, we're just going to do little z. And I have 1 over the square root of 2 pi e raised to the negative 1/2 little z squared. Where did we get this stuff? We said our mu, or our expected value, is going to occur at 0. And our standard deviation is going to be 1. So we get this curve, right? This is kind of the idea. And if you've had any statistics, you kind of know what we mean by a standard normal curve, probably. Ooh, it's a little too curvy there. But this is what we have. I'm not a statistician, but apparently I'm playing one in this video. This is mu, and then if I go over here and go over here, this is 1, and these are my inflection points, and -1. And so the question is, if I want to find probability, we talked about kind of at the end of the last video, is I have a bit of an issue, because if I want the whoa, I don't know how I got to white. That would kind of cool now. If I want the probability, let's say, that I pick something and it lies between maybe A and B, the problem is we don't know how to integrate this. This is not just a problem in business calculus. This is a problem in calculus as general. Not a problem, really. I hate saying that it's a problem. But it's something that is difficult to do because this guy we don't actually know the antiderivative of. So how do we deal with this? So what we do is, what people have done is they've done some numerical methods for finding this integral. And we didn't do a lot with numerical methods, but we talked about some with the Riemann sums. There's some stuff out there like the trapezoid rule and other things that we can use. So we use these methods to come up actually with a table. So what I want to look at, and here, this guy right here, if you actually put in 0, for z, this is a little bit less than 0.5. I just wanted to point that out. So what we kind of talked about at the end of the last lecture is we are going to define this new kind of function. And we're going to define this new function to be called a. And a of z is just going to be the probability, okay, of, taking this random variable. Oh, this should have been a capital Z up here, sorry. Of selecting this random variable between 0 and little z. So, if I want the probability that I select something and it's between 0 and 4, then little z would be 4. So we're just using a little z to kind of talk about that. And what would that look like? Well, that would be, again, what does a definite integral give us? We remember, of course we remember. That would give us the area under the curve from 0 to, whatever that little z is. Another interesting point about this that we got to at the end was that if I go from negative z, this would be the probability, okay, because we can have negative numbers. And we're dealing, I live in Wyoming. Maybe we're dealing with negative temperature values. It did snow yesterday, but we weren't negative, so that was nice. And if you look at that one, let me use a different color here. If I look at this one, that would just be this part right here, okay, to negative z. But if you notice, this distance right here and this distance right here is the same, and this curve is symmetric about the y-axis. So that means that this area right here is exactly the same as this area. So what we're going to, the reason we need to talk about that is because we're going to see when we're going to use a table to calculate these, I don't need to worry about the negative because I actually can just take the absolute value. Okay, so we need to do a couple examples of this. And the table I am talking about, I'm going to pull this up right now. So this is the table that I'm talking about, and this is in your book. It's in the appendix. It's it's technically page like A1, but it's like 592, I believe. The page right before it is 591. And if you see here, this guy here gives you the area, and it just kind of describes what this is. I wonder if I can, oh, now I'm writing on it. All right, let me zoom in just a little bit. So if you look at this, what this is going to give us is the area between 0 and whatever my z is. And my z here is, you know, let's say I want my z to be 1.4. So I come down, or 1.41, let's say. So I come down to 1.4. If I just want 1.4 itself, I go 1.400. So this is going to be the area under the curve, under my standard normal curve, between 0 and 1.4. If I wanted 1.43, I would come over here to this third one here, and I would look at the 1.43. So I hope that makes sense. You're going to get good with this standard normal table. Okay, so let's do an example of this, and then we'll do an actual example. Just want to get a example of using this chart. So let's let z, my z's are horrible, be a standard normal variable. So this is important. This chart is only for standard normal variables. Okay, normal random variable, but compute the following. So I just want us to get used to this chart. And we're going to do an example where maybe we don't have something that's a standard normal variable, and how do we get it into that? So let's say I want the probability that I select something at random and it lies between 0 and 2.34. So this is the same as saying I want the area under the curve, under the standard normal curve, from 0 to 2.34. Okay, so you're going to come to this standard normal, this guy right here. I am going to go to, so I want 2.34. So I'm going to come down to the 2's. I'm going to look at the 2.3. Whoops. I'm going to come down here and see if I can do this. I'm going to look at the 2.3, and then I want 2.34. So I'm actually going to, so I'm going to look at this line right here. This is my 2.3, and then I'm going to come down to the 2.34, and I'm going to grab that guy right there. Okay, so again, 2.3, that gives me my ones and my tenths place. Now I need, if I want my hundredth place, that's hard to say, I come over here and I get 0.4904, and that's it. Isn't that cool? So what is the area under that curve? It's 0.4904. And again, that's a probability, right? So the probability that I select one of these guys at random and it lies between 0 and 2.34 is about 49%. Whatever this random variable is giving us, right? We don't know what it's giving us, but this is just for an example. So let's try another one. What is the probability they select a random variable and I get a negative 1.8, or it's between a negative 1.8 and 0? So this would be a of a negative 1.18, but remember what we saw in that previous one, it's symmetric about the y-axis, so that's still the same as the area under the curve of just 1.8. I don't have to do the negative 1.8, so again, I'm going to look back here. I'm going to, I want 1 point, what did I say? 1.18, I believe. Oh, now I'm opening up documents. That's not what I wanted to do. Oh my goodness. Sorry, you guys. Close. Okay, it's working on it. All right. Okay, so let's pick a different color, I guess. I don't know. It doesn't really matter. So I want 1.1, right? So what was the number I was looking at? I was looking at 1.18. Okay, so I want to come up to 1.1, and then I'm going to take this line. I'm going to come all the way over until I find 8. So I'm just going to look at that whole line. And there is my 8 right there. Whoa. So I get I think it's 0.3810. And of course, 0.3810. I have, let me see if I got that. 1.18, something different in my notes. 1.18. Yeah, 0.3810. Did I write that? Yep. 1.18. I don't know what I was doing in my notes, but okay. So And of course, I'm not gonna make you memorize the standard normal table. I will be giving you the standard normal table for the test and everything. So use this. It's in the appendix of your book, page 592. Okay, well, page A1, but it comes right after 591. Then I want to show you another one here. So what about this one? What is about the probability that Z is greater than 0.3? So this can be a little bit tricky, right? Because I want Z greater than 0.3. So if I look at my curve, and if I just draw myself a picture, a lot of times I can see what I want. So, you know, wherever 1 is, I'm going to just put, I don't really care. I'm going to put 0.3 right here. And I basically want all of this area right here. Well, the problem with that is I can't really go from 0.3. Well, first of all, the function A is from 0 to something, right? So I'm going to have to figure out how am I going to do this without, you know, without knowing to go to infinity. So the idea here is if we go, we know that this is a density function. So if I took the area, right, from minus infinity to infinity, it must equal 1, right? If I take the area under this whole thing, it must equal 1 because this is a probability density function. So if I took the integrated under this entire thing, I know it's going to be 1. So what does that mean? That means that, whoops, if I take, oh, I just closed what I needed, the probability, right, between 0 and 0.3, okay, so let me color that. This part right here, plus the probability where Z is greater than 0.3. Okay, so anything bigger than 0.3, that must equal 1/2. Because I know that the entire thing is 1, but if I'm only looking at this side of the curve, then I know that that purple plus the yellow must equal half of that. So this actually isn't too bad. So now, why is this going to be helpful for me? Because this right here, I know I can find. This guy right here is just going to be A of 0.3, which I can use my chart then to do that. So I just write this out, equals 0.5. So how then do I find that probability that Z is greater than 0.3? I just take 0.5 minus A of 0.3. Okay, I'm gonna pull up this picture really quick. Okay, so again, what am I doing here? I'm going to take that 0.5, which is the area under half of that curve, and I'm going to subtract the area under 0.3. So I'm going to come down to 0.3. There's my 0.3 right there, and I don't want any hundredths place, so this is going to, wow, that was horrible. That's 0.1179. So what do I get here? Oh, sorry, I'm going to squish this in. 0.5 minus 0.1179. Okay, and that's going to be my probability. So 0.5 minus 0.1179 is 0.3821. And again, where do they get all these numbers? They do some pretty awesome math to do all of that. Okay, I hope that makes sense. That can be a little bit tricky figuring those out. Let's do one more really quick. We'll go back to this guy and clear that guy out. Okay, yeah. He always gets mad at me. I think this is part A, B, C, D. What were we on? Were we on C? I think we were on C. Let's look at D. What about the probability that Z lies between 0.1 and let's say 2.53? So again, this is kind of going to be a little bit different. There's my curve, pretend. And I want to go from 0.1 to 2 point, this isn't to scale here, but this is the area I want. And all I know, the thing that I am given is that I know the area from 0 to anything. So what we do here is we just take basically the area up to 2.53, right? So that would be this entire area here. that would be the 2.53. But what part don't I want? I don't want this part. So if I take away the purple part, so the purple part I don't want. What is the purple part? That's just the area from 0 to 0.1. So again, this right here is 0.1. This is 2.53. So how do I get that? I just take the whole area to 2.53. I subtract the area to 0.1, and that gives me the area in between 0.1 and 2.53, which kind of makes sense, right? If you want the difference between two numbers, you subtract them. And if you do that, so let's again find 2.53. So 2.53, so 2.5, I'm going to look at this guy here. Here's 2.5, I'm going to come over until I get to 0.03, so I get 0.4943, so 0.4943 minus the area under 0.1. So 0.1 and no 100ths, that would be 0.0398. I hope you guys can see that. Okay, so I get 0.4943 minus 0.398, and my probability there is pretty small, 0.0963. Okay, that seems a little bit off. Let me make sure I did that right. Why did that seem off to me? Okay, so this is really good. That seemed a little bit off to me because I know this entire area is 0.5. And the 0.1 to 2.53 is actually a pretty large part of the area. So I know that this number, well, it's not going to be super close to 0.5. It's not going to be as close to 0 as we had there. So I had this wrong. This was 0.3821. So think about your answers, right? Think about, does this make sense? That is such an important part of being good at math, is understanding, does this make sense? Because look at this guy. Out at 2.53, we are almost at 0.5, right? And then we're only taking a pretty small amount of the area away. All right, last one, and then we'll do one more example, and then I'll be done. 17 minutes, so this is going to be, yeah, we'll be fine. You guys are having fun. Aren't you having fun? I'm having fun. Negative 0.57, okay, to 1.95. This one actually isn't going to be too bad. What you just want to look at, if I look at this here, if I want negative, let's say it's right here, negative 0.57, all the way to 1.95. Well, what I'm going to do here then is I'm just going to take this area right here, and what am I going to add it to? I am going to add it to this area right here, okay? So how do I get that area right there? That's just A of negative 0.57, which we know is just the same as 0.57. And then I'm going to have plus, and how do we get that yellow area? Ooh, this is a 1.95. And then we're just going to rewrite that as the area of 0.57. Okay, plus the area under up to 1.95. And I'll let you do that on the table because I would like to get to one of the next problems that's quite important. Okay, I hope that helps. Hope that makes sense. Okay, so here's an example that we need to do. So a metal flange, I think that's how you say that. I think I looked this up and it's like a part on a truck. On a truck must be between, what do we have? 92.1 and 94 millimeters long to fit properly. Okay, I'm not going to write that, but to fit properly. So the lengths, so this is just an example of a standard normal variable, okay? The lengths of the flanges, I don't think I'm saying that right. That's okay. Supplied to the truck manufacturer I'm going to abbreviate that a little bit, are normally distributed. So that tells me it's a standard normal curve. Okay, that's what that's saying. That's saying that its probability density function is going to be a standard normal curve. Well, we're going to have to get it to that. With mean mu, okay, so the mean length of any one of these flanges, I don't think that's how you say it, is 93 millimeters, and then it has a standard deviation, okay, of 0.4 millimeters. Okay, so this is all the information that we're given. And what we want to know, well, I think this is the only part we're going to do. I'll let you look at the book for other examples, but let's just, the question I want to ask us is what percentage have an acceptable length? So the question here is, if I've been given this order of these flanges, flanges? I'm gonna just say parts. If I've been given an order of these parts, how many of them have an acceptable length, okay? Based on what I've been given. So what we want, sometimes I like to state what I want, not that that comes true in life, but in math it does. I want the probability that I select any of these x's. I'm gonna let x just be, it's a normal distributed random variable. Okay, it's not standard yet. I'm gonna make it that though. I want x to be between this 92.1 and 94. Okay, so what does that mean? That means I want to take the integral from 92.1 to 94, and then let's go back to that normally distributed function, right? Density function. I would have, so remember back in that first section, I would have sigma, so there's my sigma, times the square root of 2 pi, so look back at your notes, times e to the negative of x minus mu, which is 93 in this case, quantity squared, all over 2 times sigma squared. Okay, so this is getting a little crazy. Dx, okay? All right, I can't integrate this. I don't know how to integrate this. So I have to change this into be a standard. I want this to become a standard normal variable so I can use my cool appendix, my cool chart. So what I'm going to do is I am going to do a little bit of work here to force this to happen, okay? So I'm going to let z, it's kind of like substitution. I'm going to let z equal x minus 93 over 0.4. So basically, I want to get negative 1/2 z squared, right? So I want to rewrite this. So then I have to figure out what my dz is, right? So dz here, if I think of this as 1 over 0.4 times x minus 93, the derivative of x minus 93 is 1, so I get 1 over 0.4 dx. Okay, so if I replace this dx, then what is dx going to be? Well, no, we're good. No. So I have dz equals 1 over 0.04x. So what is dx? Dx is 0.4 dz. Okay, I hope this is making sense. What I'm trying to do is I'm trying to get this into our standard normal function. Remember our standard normal function, I'm running out of room, is 1 over root 2 pi e to the negative 1/2 z squared. So if I look at this guy right here, I could rewrite this guy to be a negative 1/2 times x minus 93 over 0.4 quantity squared. Do you see that right there? So what I'm doing here is I'm just wanting this guy to be z, okay? Okay, so I'm gonna rewrite this really quick so that we can kind of see what's going on. Maybe just to make this lecture a little bit longer. Oh, it always gets so mad at me. Okay, so again, what did we have here? We had, not yellow, we had, what, 92, let's look back at this really quick. So I had 92.1 to 94, right? So 92, oh my goodness. 92, okay. Oh my goodness. Sorry about this. Okay, don't want layer 2, I want layer 1. There we go. 92.1 to 94. We had 1 over, let's see, 0.4 square root of 2 pi e to the negative 1/2. I'm going to rewrite this a little bit, right? Like I kind of talked about here, over 0.4 quantity squared all dx, and we're making a substitution, remember. So I am going to let z equal that x minus 93 over 0.4, and then we kind of found that 0.4 dz would replace dx. So look at what happens here. This is actually pretty awesome. So I'm going to get, look at when this guy goes in for dx, when this guy goes in right here, this 0.4 and that 0.4 will cancel. That's lovely. So I get 1 over root 2 pi, which is what I wanted, e to the negative 1/2, and then this whole thing just becomes z. Look at, guys, we're doing substitution in kind of a different way, and then I get dz. Now notice I haven't put my bounds. Remember, what are those bounds for? Those bounds are for x, so we need to change. So when x is 92.1, what is z? Well, I'm going to plug that into here. I would get 92.1 minus 93 all over 0.4. So when x is 92.1, I'm going to put this into my calculator. 0.1 minus 93 divided by 4. I get a negative 0.225. And when x is 94, z is 94 minus 93 divided by 0.4, so that's 1 divided by 0.4, which is 2.5. So my new bounds then are a negative 0.225 all the way up to 2.5. Guys, remember what this is right here. This is now my standard normal curve. So basically what we're asking here is to find the probability that my normal curve, right, lies between negative 0.225 and 2.5. Isn't that great? So look at what we get. I get the area then. Remember how we're going to deal with this? I get the area of a negative 0.225, which we'll just call positive 0.225 because they're the same, plus the area of 2.5. If you don't get that, draw the picture. So what I do is I'll say, okay, here's 2.5, here's negative 0.225. If I want this area right here, I want all of this plus all of that, okay? And that's when we get to our, we're gonna go back to this, right? Okay, so I'm gonna look here. I'm gonna look for negative 225. So actually just positive 225. Okay, so there's 0.2. Let's see, where am I at? Sorry guys, 225. So I'm gonna get pretty close. Whoops. I can't quite get, whoops, all the way at 225, but I could get 0.22 or I could get 0.23, right? So maybe right here. Let's use that one. We'll round up a little bit. 0.0910. So this equals 0.01 plus 2.5. So again, go down to 2.5. I don't want any hundredths. 0.4938. Wow, that's pretty cool. Okay, oh, I think I messed up here. Hold on, you guys. Oh, I did. I thought that was looking a little off. I divide by 4 instead of 0.4. Okay, that makes me feel a little bit better. This guy right here, the decimal place should be right there. I knew that was not quite right. So, again, I make a mistake with simple arithmetic. Story of my life, people. Story of my life. This will be much better. This is 2.25. Okay, so negative 2.25, negative 2.25. Okay, so let's go back to here. Sorry about that. 2.2, there's my 2.2, and I want to go all the way over until I hit 5. 0.4878. Sorry about that. 0.4878. But you know what? Everyone does it. All right, so look at what we get here. I'm going to take 0.4878 plus 0.4938. It's going to be pretty close to 1, you guys. We get 0.9816. What did that all mean? I don't know after all that. 98% of the flanges, whatever you call them, are acceptable, or are in between, right? The 92 and the 94 are of acceptable length. All right, you guys, there's a little bit more to this example, but I've hit 30 minutes. So what I would like you to do is look at the example in the book. If you have any questions, of course, start working on the homework. Look at the fun sheets for more examples. These can get kind of tough. So make sure you start on these kind of early. Hopefully, if you're already watching this, then you have gotten a good jump on it. All right, let me know if you have any questions.